similar to the last announcements. So if you're interested in attending all these sessions, please subscribe to the mailing list. So in the chat, I have posted all the announcement and the link for subscription of the mailing list. The talks will be recorded and available on this YouTube channel. So I will share that by email also once. Also, you can give feedback about the talk in the Google form, which is shared. We have a Discord channel where we discuss other things like job opportunities and other like interesting thing happening in data science around the world. So you can join them and have a discussion with other folks and socialize with other folks in data science in the group. Also, if anybody of who you are attending and have an interesting topic to speak about, you can always email me or Corey. So the email IDs are given in the chat. So have a look. Now let me introduce our speaker. So I'm excited today to um, join Ayan for talk. So he's a postdoctoral research fellow at the Stanford Intelligence System Lab at Stanford University. His research interests includes multi-agent system, robust machine learning, and decision making under uncertainty. He was awarded 2019 CARS postdoctoral fellowship by Center of Atomic Research at Stanford. He completed his PhD at Vanderbilt University Computational Economic Research Lab, and his PhD was nominated for Victor Lesser Distinguished Dissertation Award 2020. Whoa, that's good. His work on urban emergency response management has been covered in the Government Technology Magazine, Financial Times, or multiple global smart city outlet, and also received the best paper award at ICR AI for social good action. So there's lots of good and heavy achievements. Before wasting more time, I would like Ayan to speak and tell about some of his work, and yeah, how he's helping. It's an interesting work because it has social connection also, and I hope all of you will enjoy the talk. So Ayan, hand over to you.
Thanks a lot, Vivek. Good morning, everybody. Let me try and figure out how this thing is working. Okay. Thanks, Vivek, for the introduction. As everybody, all of you know by now, I am Ayan. I'm a postdoc at Stanford, and I'm going to talk about robust incident forecasting and response. We covered pretty much all of my background. I am a postdoctoral fellow at the CARS Institute at Stanford, which is the Center of Automotive Research. I work at the Stanford Intelligence Systems Lab. Before that, I was a PhD student at Vanderbilt. Broadly, my interests, the technical interests are in robust machine learning, spatio-temporal incident prediction, and multi-agent systems. And I apply these things overall to AI for good. I'm very interested in understanding how smart cities are being developed, how we can do smart emergency response. Off late, I've been very interested in environment conservation. So the talk that I'm going to give today can broadly be summarized by the three words: smart emergency response. Emergency response, I mean, whether it's smart or not, comprises of two major chunks. One is the incident prediction part, which is more of the machine learning side, where you want to understand where and when a set of spatio-temporal events happen, and you want to create machine learning models for it. And then given such a model, you want to allocate resources and optimize them in anticipation of the incidents. So the work that I'm going to present is in collaboration with a lot of people. And I would just like to quickly mention them before I begin. CISL, or the Intelligence Systems Lab, is where I work. The Automotive Research sponsors my fellowship. A lot of this work is in collaboration with the Center of Research in Computation and Society, which is at Harvard, which is Professor Milind Tambi's group. Part of the work was done with the Institute for Software Integrated Systems at Vanderbilt, and Computational Economics Research Lab is my PhD lab at Vanderbilt. So I'm thankful to all my collaborators for all the work that I'm going to present. So we've had some highlights in this research. If you're interested in reading a very policy-oriented effects of our work, then these are the sources where you can find them. I'd be glad to share the exact articles And you can understand how we are trying to help cities with smart emergency response. Okay, so let me motivate, before I begin into the, before I get into the technical details, let me motivate the problem a little. This is an article from 2016, and I want you to pause for a while and look at the number that's on the newspaper article. So from 2013 to the beginning of 2016, about 100,000 elephants were killed in Africa just for the illegal ivory market, which is an enormous number. Now, there are various types of illegal activities that we are interested in predicting. One of the ones that's plaguing the United States is vehicle theft. The text is probably too small, but it says that there were about 700,000 motor vehicle thefts annually in the United States, which is again a massive number. It's the same situation with burglaries. On an average, every year, about $5 billion are lost just due to burglaries, and this is only in the United States. And I want to tie this back to poaching with a problem that has surfaced very recently. If you're aware of this very shy animal called the pangolin, which now has, for the lack of a better word, has a lot of demand in the illegal animal market. Apparently, it's used in Chinese medicines, and it's almost being hunted to extinction because, I mean, they're extremely shy and extremely elusive. They really don't run away. And so we are broadly interested in understanding where and when these incidents are happening and how we can tackle them. The part of sort of the other spectrum of emergency incidents that we are interested in are motor vehicle accidents. And I say the other spectrum because unlike crimes, accidents usually are not caused by deliberate planning by agents, right? They happen out of a set of environmental conditions. This is an extremely old newspaper clipping that I found. It's probably from the 1930s, which tells you that the United States, the country as a whole, was extremely concerned about the total number of motor vehicle killings that were happening and the total number of people who were losing their lives due to motor vehicle accidents. Now, a developed nation, you would imagine that they have solved the problem in, you would imagine that we have solved the problem in like 100 years. It turns out that we have not. This is a significantly recent article from 2014, which tells you that just by road accidents, about 30,000 Americans die every year. If you can read the last line of the article, it says that it's the #1 cause of death for Americans under 35, which means that as far as the youth of the country goes, this is the leading cause of death. The other striking visual that I would like to share with you is this image that we created from Tennessee, which is where Vanderbilt is. If you know what the shape of Tennessee is, this is exactly the shape. So, I mean, the dots that you see pretty much covered the whole of the state. And these are points where automobile accidents have happened in the last 10 years. So you can see that the dark places are probably forests or lakes or something, but wherever there is a road, there's been an accident. And the sheer density of it is rather alarming. So now why is this happening? Now there are a lot of reasons why crimes happen and why accidents happen. But as a computer scientist, we are interested in a few of those reasons that we can help tackle. One of the most important reasons is that there is a serious scarcity of resources as far as crimes go. If we had the resources to patrol every inch of our national parks and forests, then poaching probably wouldn't have happened. But I'll show you data that we use from national parks in Uganda, which are about 3,000 square kilometers. And at the time when we had collected the data, there were about 40 patrol officers. So that tells you, and these are forests, it tells you how enormous the mismatch is between the total number of targets, so to speak, that need to be protected and the total number of defenders who are trying to protect these targets. The other issue is that we've spoken to a lot of emergency responders in the course of the last 6 years, and it turns out that a lot of dispatch strategies are very ad hoc. For example, the most common dispatch strategy that is used in the field is that when an incident happens, the closest responder is dispatched. Now, this is both good and bad, and I'll get into this a little later in the talk. But as a bunch of computer scientists, we can sit here and understand why such a greedy policy is myopic and not optimal, with optimality being measured in the sum of response times across some horizon. The third problem is that there is a real lack of principled incident prediction approaches. So what a lot of approaches do is that they would create a heat map of some sort, and they would target the area that has the most heat, so to say, in the heat map. And it is repeatedly found that, especially with crime predicting algorithms, that they're not better than untrained humans. However, they can have a lot of bias. So it actually makes them worse in some sense than untrained humans. And finally, the problem is that what most of the machine learning pipelines forget to address, and what is going to be the major area of discussion of this talk, is that criminals are smart. So for example, poachers are not going to go poach in do illegal poaching in an area which has forest rangers moving around. And we'll see how that problem manifests. So we can broadly summarize the problems that we have identified in order to create an emergency response pipeline as the following problems. So first, we want to identify where incidents happen in time and space. Then, given that model, we want to allocate depots and responders. So think of depots as something like fire stations, and responders is something like either forest patrol officers or ambulances, and so on. Then we want to create principled algorithms to dispatch these responders when incidents happen. So when you get a call, a 911 call about an accident, you want to dispatch a resource, but in a principled manner, which is which makes sense algorithmically. Then we'll, as I said, in this talk, we'll look at the robustness of forecasting methodologies, in the sense that how can we ensure that the attacker or the people who have the malicious intent of committing crimes are not changing their behavior. And if they are changing their behavior, then how can we adjust our prediction algorithms in accordance with that? And finally, we want to make sure that all these algorithms, as far as prediction goes and response goes, are online, in the sense that as and when incidents happen, they are able to update themselves really fast. So you don't have to retrain the whole algorithm and wait for a week or something to deploy fresh strategies. So this talk is going to be about two of these problems. The first half of it, I'm going to talk about a paper that was recently accepted at UAI 2020, which is the robustness of incidents. And then I'm going to talk about some of our work about dispatching responders, mostly from the AMAS 2020 paper that we have. Okay, so let's go into exactly what the problem scenario looks like for robust incident forecasting. This is a map from a very densely packed area of national parks in South Africa. So the problem is this. Imagine that you have a bunch of places that animals frequent. Or I mean, when I say it's not necessary that the forest rangers know, and just think of this as the ground truth. This is how typical machine learning algorithms work now. You get reports of poaching from some of these areas, and you take immediate action. You deploy forest rangers in order to combat poaching, which for a short period of time works. And this is where most of the machine learning algorithms would stop. The problem, however, is that once you do deploy rangers, the poachers move. So they can go to a different area and commit the same illegal activities, but the forest rangers have to wait for fresh reports to come in. And by the time they go to these new places, the poachers would have moved again. And as I said, the real issue here is that we have a scarcity of resources. If we had enough means to protect all of these points, we would have, but then that's really not the case. Okay, so what's the formal statement here? For a given area or a given spatial area, we assume that incidents that are of concern happen at specific coordinates and specific times. So there is a definite spatial temporal stamp attached to each event. We assume that we have access to a set of these historical incidents that I'm going to refer to as D. Now consider that the entire set of spatial areas is divided into a set of equally sized cells. Cells actually need not be equally sized, but for the rest of the talk, we'll just assume that without loss of generality, everything works if they're not equally sized. And for each cell, imagine that we have a distribution that models the incident occurrence in that cell, which is measured by some random variable. Now, we have also done a lot of work about how to create these models, but that's not going to be the focus of this talk. The only assumption we make is that the distribution is convex, but I'll talk about what happens if it is not convex. But then, as we wrote in the paper, most of the algorithms that are used in the field for spatial temporal incident prediction turn out to be convex. For example, Poisson regression, logistic regression, parametric survival models, they're all actually convex. So here is how we can represent this mathematically. We have a distribution F, which measures some sort of measure of incident occurrence, which we represent by X. W is a set of features, theta is the regression coefficients. And typically what any machine learning pipeline would do is that it would try to find out the optimal set of parameters that maximize the likelihood of the given data set that you have. So the product I is over all points in the data set. Okay. Now, what happens? Imagine that we have three incidents, D1, D2, and D3, which had happened in three of the cells as I have marked. Now, what happens is that these incidents can shift to other cells. Now, we represent the collection of all such shifts by the random variable S. So for example, assume that Sij represents the attacker's choice to shift incident Di to cell Gj. Okay. Now, the way these shifts affect the random variable X is actually crucial to understand. Imagine that your random variable is the count of all incidents in a particular cell. Okay. So if D1 shifts to the cell where D3 originally was, you cannot simply increase the original count of the cell by 1 because D3 can shift somewhere else. And then D2, for example, can also shift to the cell as I've marked in the picture. So you have to individually look at all the incidents that can shift, which is a combinatorial action space. That's the point that I'm trying to communicate here. So what the attacker wants to do is that it wants the model F to be inaccurate. And the reason why the attacker wants to do this is because patrols or sort of forest rangers, the distribution of patrols is actually dependent on the model F. What people typically do is that they learn a distribution F, and then they direct patrols to the areas that have the highest probabilistic mass, so to speak. Now, here is the problem, which is actually a problem that is in all of adversarial learning. We actually do not know the true future distribution. If we knew the incidents that are going to happen, then what we would have done is we would have simply calculated all the shifts, and we would have just asked our patrol officers or forest rangers to go to the predicted points. However, we don't know that because it's in the future. So the approach that's taken in adversarial learning is actually using the dataset D as a proxy. This idea is a little difficult to wrap your head around. So what we basically do is we simulate the actions of the attacker on the historical data set. And what that means is that basically the attacker tries to minimize the likelihood of all the incidents. Let me know if this doesn't make sense, because this is sort of the basis of the rest of the model that I'm going to present. So again, quickly, this is sort of the crux of the matter. What the attacker is trying to do is that it is trying to shift its movements in a way that the predicted likelihood of the model F is the minimum. Now, there are obviously other questions you can ask. For example, this assumes that the attacker has sort of perfect knowledge of the model F in the first place. also has perfect knowledge of prior historical incidents that have happened, and it also assumes that the attacker is perfectly rational. Now, those are assumptions that are fairly common in the adversarial learning literature, and then we can relax these assumptions in a lot of ways. We can look at models of bounded rationality and so on. But for the purpose of the talk, we'll just assume that this is the attacker's objective function. Okay, so now what is the defender trying to do? The defender is trying to play a game with the attacker where, knowing fully well that the attacker would shift its locations for committing incidents based on the model F, the defender is trying to maximize the likelihood of the learned model. So basically, the defender is trying to maximize the likelihood in the worst case scenario, knowing fully well that the attacker would do everything that the attacker can to shift to places such that the likelihood of the attackers getting caught is minimized. So that's how we can represent sort of the defender's objective. Now, there are a few things that you probably note here. First is the hierarchy of the max and the min operators. Theta think of theta as the actions that the defender is choosing, which is the parameters of the likelihood model. Think of S, which is the set of spatial shifts, as the parameters that the attacker is choosing. And then there's this hierarchy, which means that the attacker actually gets to observe what the defender is doing first. This is very obvious. The defender's parameter is outside and the attacker's is inside. So this is basically, if you are aware of game theoretic formulations, this is called a Stackelberg game or a leader-follower game, where the follower actually waits for the defender to, or the sort of leader to make the first move, gets to observe what the defender has done and then make its move. So that is one of the problems that we have, which is the hierarchy of the max and the min operators. The other problem which we have, as I said, is that the set of all attacker combinations is, all attacker actions is combinatorial, and it's also discrete because the attacker is actually picking out specific locations from this set of sort of discrete finite set of locations. So this problem is not very straightforward to solve. For the rest of the talk, we'll basically talk about how we can solve this problem. Okay, so in the paper, we present two distinct sort of algorithms to solve this problem. The first one is known as RSALA, which stands for Robust Spatial-Temporal Analysis with Linear Attacks. So here is the sort of high-level idea for this algorithm. What we are saying to the attacker, imagine what we're saying to the attacker is that every time the attacker makes a shift, it results in a unique modification to the original data set. So for example, consider a situation where the original data set had 10 incidents and the attacker shifts incident 1 to say point X and incident 2 to point Y and so on and so forth. Now, a specific selection of shifts results in a specific modification to the data set. Now consider that we have access to all the manipulations that the attacker can choose from, which is actually straightforward. It's going to be an extremely large set, but it's fairly easy to calculate that set. And each such modification is being referred for the rest of the talk as a chain, and let there be a total of C such chains. The C again is an extremely large number, but nonetheless, it's a finite number. So on top, what I have is the original formulation that I had showed you. And on the bottom, what I have is the formulation based on chains. So what we are telling the attacker in the objective function is that we are giving the attacker access to all the chains. And we are simply asking him to pick, or asking her to pick, the chain that results in the lowest likelihood. If you look at the constraints, lambda must sum to 1, but then lambda can either be 0 or be 1. So out of all the sets of lambdas, like total number of C lambdas, only 1 can be 1. So the attacker basically gets to pick only one chain, which is what the attacker tries to do. The attacker is trying to pick the combination of spatial shifts that results in the minimum likelihood. Now, this, why is this formulation any better? So far, we have not done anything that actually gives us an easier problem to work with. But here is a very crucial piece of insight. Imagine that you're the attacker. you can pick multiple chains, say 2 chains, if and only if they give you the same utility. Okay, imagine that you have 2 choices, one with utility X and one with utility Y, and I give you the option of picking through these choices probabilistically, which means you can say that, okay, 0.4, with 0.4 probability, I'm going to pick option X, and with 0.6, I'm going to pick option Y. Now, if you know the utilities of X and Y, you'll always pick the option that gives you the higher utility, which means that you can pick 2 options only if they have the same utility, or else you can just transfer the probabilistic mass from the lower utility option to the higher utility option and maximize your utility even more. So what that means is that we no longer have to constrain lambda to be either 0 or 1. We can ask the attacker to pick as many of the chains as the attacker wants, but crucially, that does not affect the utility or the value of the objective function that the attacker lands at. So we can drop the integrality constraints, which basically gives us this optimization problem. It's the same problem, except that we've dropped the integrality constraint. Now you can probably understand where I'm going with this. You have a max and a min, and then the min problem is now linear. F we know is convex. It has no integrality constraints. So it's very straightforward to take the dual of that problem. So by taking the dual of that problem, we achieve 2 things. First, instead of having a max and a min, we now have a max and a max, because taking the dual of the min problem gives us a max problem. And the other problem which we had, which was that C was an extremely large number, but now the set of this extremely large number is being transferred to the constraint set. So we now, instead of having C terms in the objective function, we now have C constraints, which again, the most obvious thing to do here is to do constraint generation. So here is what our Sala does. It first drops the integrality constraint, takes the dual, and then does dynamic constraint generation. So what dynamic constraint generation does is that we start with an arbitrary set of like 1 constraint. And then for that constraint, we calculate the attacker's best response. So if the defender would have chosen a specific theta, what would the attacker have done optimally? And that gives us another constraint. Basically, it gives us another chain. So because it gives us a set of modifications that the attacker is aiming for, and then we can add that constraint. And we can keep adding these constraints. Now, well, obviously the issue is that what if in the worst case, we have to add C constraints, which is obviously an issue. But then if you've done constraint generation, you would know that constraint generation methods converge fairly fast. I mean, in our case, with more than like hundreds and thousands of constraints, this converges in like 20 iterations at max. Okay, so this is 2 small comments about this method. First, we are actually solving the problem completely, okay, which means that it doesn't matter how many constraints you have to add, you'll always get the optimal solution. I mean, within some exogenously specified epsilon, which you can treat as your tolerance. The other issue, or the issue with this process is that it is slow, because although it converges after 20 iterations, at every iteration, you still have to solve the updated set, the optimization problem with the updated set of constraints. So in order to trade computational time with accuracy, so in order to trade off computational time with accuracy, we came up with this other approach, which we refer to as ADGRAD, or an acronym which stands for adversary-based gradient descent, which what basically does is the same, but there is no need to solve the optimization problem at each step. What it does is that, again, it starts off from an arbitrary theta, which I'll tell you how you can choose a good starting theta, but it basically starts off with a set of defender parameters. And using that defender parameters, it takes 1 gradient step based on the actions of the attacker. And then it just keeps doing this. Once the attacker takes a step, you can compute the optimal defender, the optimal theta for the defender, and then you can again compute the actions that the attacker would have taken, and you take 1 gradient step again. And you keep repeating this till standard gradient descent convergence norms. So I'll actually quickly pause for a while and ask if anybody has any questions, or if not, then I can go on and show you some sort of simulation results that we have. Okay, so I'm just going to go ahead. Okay, so actually, before I show you the simulation results, I haven't really shown you how we can formulate these optimization problems. So F was very generic so far in our application, but then we can actually replace it with any standard regression model as long as it's convex. Now, the reason for convex is obviously, I mean, having strong duality results. Everything works if the function is not convex, except that we no longer are able to guarantee that our salad leads you to the optimal solution. I mean, AdCAD works perfectly fine, though. And you'll still get a solution from our Sala, which is better than having no robustness, but then it's not guaranteed to be convex. So let me quickly present how we can use this to do survival modeling. So what happens in survival modeling is that the random variable X denotes the time between incidents. So given a bunch of arbitrary incidents, you want to learn a distribution of the inter-arrival time. So think of it this way, if an incident has happened right now, you want to be able to predict when the next incident can happen. So, okay, how do we look at the set of attacker, spatial shifts? So consider a set of 3 incidents ordered in time. Imagine that D1, D2, and D3 happened one after the other. And then they can shift. The attacker can choose to shift D1, D2, and D3 anywhere. Now let's focus on G5 specifically, which is the center grid. So both D1 and D2 can shift to G5. And what that gives us is 3 sets of consecutive incidents. Our consecutive incidents could be D1 and D2. They could be D2 and D3. But also note that they could also be D1 and D3. The reason for that is D3 could shift somewhere else, okay? So, which means that you can basically get all combinations of these 3. But the crucial point to understand here is that incidents that are removed from each other by a different incident temporally, so basically look at D1 and D3 and understand that D2 is in between them, all such incidents can only occur as consecutive incidents if the middle incidents do not happen in that cell. So D1 and D2, D1 and D3 could be consecutive if D2 moves somewhere else. Okay, so this is how we can formulate the optimization problem. It's actually based on the one insight that I just gave. You look at all combinations of potential incidents, all pairs, and you make sure that for the likelihood term, which is the one that you see on the rightmost of your screen, the likelihood term is non-zero if both D1 and D3, as in the example, they happen, but D2 does not happen in that grid, which is why there's a 1 minus. So if D2 does not happen, then the middle term 1 minus is just reduced to 0. Okay. Okay. So that is pretty much it. You can take any arbitrary sort of regression model and you can frame an optimization problem. For example, this is the Poisson regression formulation. It looks sort of technical. It's actually very simple. All you have to do is embed the regression, embed the spatial shifts into the regression model, and just make sure that everything there is no violation of constraints. For example, the attacker can choose to move one incident to only one place, and it can only shift one incident once, and so on and so forth. And then what you do is you take the attacker problem, put a max next to it. That gives you the overall defender problem. You drop the 0-1 constraints. You take the dual. You get a max over max, and then you can, as I presented, 2 ways of solving that problem. Okay. So we evaluated our approach using 2 data sets. So the first one is courtesy of the Uganda Wildlife Authority. We got our data from the Murchison Falls National Park, which is about 4,000 square kilometers. We used a total of 3 years of data for training and 1 year of data for testing. Now the data that is there in the park is marked as a binary response. So people, Forest Patrol goes out and they don't, for example, see how many animal carcasses they found or how many snares they found. They only mark whether they find a snare or not. So they are binary responses. A total of about 18,000, out of which 2,600 were positive, which means showed evidence of poaching, and the rest were negative. So for computing the feature space, we looked at, for each incident, we looked at the closest boundary for the national park, the closest village boundary. We looked at where the closest water source was, the closest mineral lick location, which are like salt locations where animals come to eat salt. We looked at past animal sightings for animals like buffalo, deer, giraffe, and so on, and a bunch of other geographic features like what's the vegetation type, what's the elevation, and so on. We also looked at urban crime, specifically assault and burglary data from Nashville, a total of about 7,000 assault and 2,100 burglaries. It's a comparatively smaller data set, but nonetheless. But before I present you the results, there's one small caveat that I'd like to mention is that so proactive policing in general has a lot of ethical issues, even without somebody trying to model robustness. What modeling robustness is basically doing is that it is diversifying the spread of patrols. Now, if the crime data you have is already biased, then these biases would feed in to your prediction algorithm, and as a consequence, this whole robustness approach that we have. Now, that might not be an issue for poaching, but that is surely an issue for urban crime. So the objective of using urban crime data to evaluate this is not to say that, hey, this can be deployed in a city, but sort of to just look at how the models work with real world data sets, which have, a lot of noise and so on. Okay, so here are the results. In all the, I'd not go into what the individual bars mean. Basically, everything blue that you see is the standard machine learning regression approach. Everything red or sort of orangish is AdGrad, and everything, the other color beigeish is our Sala. So the key takeaway message here is that, and by the way, so I mean, unless you've, in case you've not noticed, the y-axis is the negative log likelihood. So actually, the lower the bars are, the better it is. So the key message here is that in sort of all the methods and all the data sets that we use, it's fairly easy to understand what's going on. The least robustness is sort of achieved if you do not do any spatial shift modeling. AdGrad sort of achieves a little bit of robustness, and in some cases, a lot of robustness. For example, the C plot, it does extremely well in comparison to the standard vanilla approach. But then obviously our Sala is guaranteed to be optimal, so it does the best in all the three cases. But okay, I wanted to show you a graph of the running time, which looks like I've misplaced it. But then anyway, the running time comparison is actually as straightforward. Our Sala takes a lot more time to train. In some cases, it took a day, for example. However, the gradient-based approach is very quick. It would take maybe 30 minutes or less to train. Okay, but it's crucial also to understand that robustness of machine learning algorithms is not gained for free. Okay, so we must be sacrificing something in order to gain this robustness. And sort of what are we sacrificing? So the graph that you see here is generated by distributing the set of cells in the area under consideration into 10 bins. And the bins are sort of arranged by the frequency of incidents that happen in them. So bin 1 has the lowest frequency of incidents, and bin 10 has the highest frequency of incidents. And what we are plotting is the difference that the robust algorithms predict with respect to the vanilla approach. So what we basically see is that for all bins, the difference is positive, but for the highest bin, the difference is negative, with one exception. So what that means is what's happening is that these methods are actually smoothing out the distribution. They're taking some probabilistic mass from the very dense areas, and they are spreading it to the areas that maybe have not seen as much incidence, but based on our model of spatial shift, are likely to see some. But then it would be a little worrisome if this magnitude was a lot, because not all areas, it doesn't matter what exogenous model of spatial shift you have, not all areas provide the same opportunities, for committing these incidents. So we still want the extremely dense places to have the most probabilistic mass, but we want the other places to have sort of somewhat extra mass. So what we basically observe here is that the rate of incidence that is shifted for R is close to 0.004, which is not a lot. So we are doing good there. The other thing that is very crucial is that the shift model has to be exogenously specified. So you can imagine that the attacker can shift to anywhere in the spatial area under consideration. But that's oftentimes not the case, because the attacker also has a limited budget. For example, a poacher probably would not, walk 300 kilometers to go to a different forest or different national park. So what existing theories of incident occurrence have showed us is that these incidents, even when shifts happen, they happen very close to the original place of the incident. So what we basically did is that we simulated different budgets the attacker has. And when I say budget, I mean the spatial budget. So the leftmost plot that you see is having the lowest budget, which means the attacker can only shift to the cell that is right adjacent to where the original incident had happened, and then we gradually increase it. So what that also tells us is that if somebody naively tries to use this model using a very large shift, thinking that that will get robustness, that will provide robustness against all sorts of shifts, the model is actually rendered useless, because the robust model thinks that the attacker can actually go anywhere to commit crimes and sort of, for example, poaching, and then it places a very high sort of mass, sort of equal mass at all places. So these are some sort of caveats or finer nuances that come with this model. Okay, so that lets me that brings me to the end of the first half of the talk. The second half is not as long, but then I can take questions about the incident prediction approach now, or otherwise I can go after the sort of the response part of the talk.
Any questions?
Okay. Cool. I'll just go over to the next section then. Okay. So this is going to be a shorter section, but I'm going to talk slightly about multi-agent emergency response, but crucially multi-agent response that is decentralized. So this is sort of a small visualization of accidents happening in Nashville every 12 hours. Nashville is sort of the heart of the plot that you see here. Now, if you can see my mouse, this is where the very sort of downtown area of the city, there are a lot of incidents, but then the rest of it is actually fairly scattered. And there are times when there are a lot of incidents, there are times when there are not as many incidents. So the problem of emergency response in case of traffic accidents is that whenever one of these incidents happen, there's a 911 call that gets associated with it. And then the job of the fire department, which handles ambulance response in Nashville, is to dispatch an ambulance as fast as possible and as quickly as possible to the scene of the incident. So that's broadly the problem. Okay, so this is actually a very complicated, the urban dynamics are very complicated. There's a lot of traffic, things like weather, for example, affect response times. one road closure, one construction, the number of sort of exogenous parameters that affect our model are a lot. So how do we deal with such scenarios? The first thing we do is we abstract away and we only look at a few things that are very important to us. But even then, it's a continuous time process. Imagine that an ambulance was at coordinate X, Y, but then in order to dispatch an ambulance, you want to understand where all the ambulances are. So even if it moves a little, we would have to keep track of it. So it's changing. It's a continuous time process. It's changing at every instant of time, which makes these models extremely hard to deal with. But a common trick in these problems is to sort of close your eyes when there is no decision-making state. So if there is no accident that is happening, we sort of close our eyes and we say, we don't really care what's going on in the world. But as soon as there is an incident that gives us the chance to make a decision, that is only when we observe the world. Now, the nice thing about this is, imagine that the x-axis is time and the y-axis is state. So by construction, when we observe the world must agree, our sort of model of the world must agree with the real world, because there's only sort of one sort of temporal coordinate, and we are only turning our, imagine a switch on and off in time. Okay, so this sort of helps us get rid of this large continuous state space, but there is still a different issue, which is that if you try to model this as a Markov decision process, the problem with sort of continuous time MDPs is that the time distribution that leads from one state to the other has to be memoryless. So it's mostly modeled as an exponential sort of distribution. If this doesn't make sense, it's actually fairly straightforward, and I can talk about this more in the question answer session. But the issue is that these problems cannot be modeled by memoryless process, because ambulances travel from one place to other. And while you can model everything else by an exponential distribution, for example, you can model the rate of incident occurrence by a Poisson model, or the time between incidents by an exponential model. There's just no way you can model, travel time in a memoryless way. They're sort of mostly, a linear model. The total distance you have to travel can be used like a proxy for the total time you take to travel. So the way this is dealt with is that we model this as a semi-Markovian decision process, which is in every other way a continuous time Markov decision process, except that this density T is no longer memoryless. So you have a bunch of states, you have a bunch of actions that you want to optimize over, you have a probability sort of distribution, which tells you if the world is in state I and you take action A, what's the odds of you landing up in state J? This capital T distribution tells you that if you do this, if you take an action at state I and land in state J, what's the time that it takes you from going from one of the states to the other? And then there's a reward function. So the sort of the canonical issues with such processes is that in urban areas are extremely complicated. So it's very hard to estimate the probability P in closed form. And then obviously this is, as I said, it's a continuous stochastic process, continuous time stochastic process with a non-memoryless transition. So what other people have done, and then other people referring some of my previous work as well, one thing that you can do is you can just ignore that this T is not memoryless. And you can say that, okay, for sort of theoretical convenience, we are going to assume that T is always memoryless, and then you can transform this SMDP to a continuous time MDP and you can directly solve it. So that was the sort of the state of the art. And then we wrote a paper about sort of and presented an algorithm called SimTrans, which took into account that real world distributions are not memoryless. But what we did instead was that we built a simulator of the city and we repeatedly ran it to estimate P. And then once you have P, you can transform a semi-Markovian MDP to like a discrete time MDP, and then solve the discrete time MDP as you would solve, any standard MDP. The issue with that is, and the state space is enormous for this problem, and estimating P is really, really, really hard. I mean, you have to run this forever and ever. The paper that we wrote for AMAS, it took us 24 days and on a fairly modern server, say 128 gigs of RAM and 56 cores. It took us about 24 days to come up with a reasonable policy. So obviously that doesn't work, because you can train your model for 24 days, then imagine that one ambulance breaks down. So the problem definition changes, and then you have to retrain your model for 24 days again. So, I mean, obviously it has zero practical applicability. So what we did was we came up with another approach where we, instead of saying that, we are going to find the optimal action for all states, we said that we are only going to find the optimal action for the current state. So given that an incident has happened, we're quickly going to run a Monte Carlo tree search and come up with an action that is reasonably promising. Okay. So while that solves some of the problems, okay, actually, if I go into what problems it doesn't solve, these are some sort of visuals from the paper that I mentioned here. The first sort of crucial piece of the puzzle is to come up with an incident prediction model. So the figure you see on the left is the troop distribution, and the right is the distribution that we predicted using our models. And then once you have this model, you can learn Monte Carlo tree search, because this prediction model helps you build a simulator. Now, the problem with this is, even after coming up with this approach and talking to a lot of responder organizations, we figured that none of these approaches were actually being implemented in the field. And we are not the only ones to have created an extremely principled and theoretically sound dispatch approach, and then have gone to first responders and they've said, I mean, it's fine, and we're interested in collaborating, but we're not going to deploy this. And what we slowly figured is that it's a result of the moral constraints within which first responders operate. So once an incident happens, it doesn't matter if the incident doesn't sound serious from the 911 call, or if you think that greedy response is never going to lead you to optimality in the long run. First responders simply have to dispatch the closest ambulance, because I mean, there are certain legal principles, but just nobody wants it on their conscience. It's never going to happen. People can come up with all the principal dispatch algorithms they want. First responders will always dispatch the closest responder. Okay, but then, so how can we actually solve the shortcomings of ad hoc dispatching? So we began asking the question then that if we cannot implement algorithmic decision making after a call comes, when can we implement it? So this is how a typical 911 response chain works. You deploy resources, a call happens, and then very quickly you use some sort of algorithmic decision making to come up with a decision. You dispatch the responder. The responder then returns to its depot at its fire station. Then again, a call happens, and then again, you compute a decision, and so on and so forth. So our conversations with first responders told us that these two sort of red arrows are absolutely, you cannot touch them. This is where there is absolutely no room for negotiation. Responders have to be dispatched as soon as possible. So even if your approach takes, 20 seconds or 30 seconds, lives are at stake. Nobody's going to do that. So what we instead did was that we tried to come up with an approach that does algorithmic decision making after an ambulance finishes response. So we figured that there's actually no need for the ambulance or a fire truck to come back to the fire station. There are lots of parking lots in the city, which fire departments actually rent. So we can, or for example, think of a university parking lot or a church parking lot, which is fairly easy for first responders to collaborate with. So instead of having a decision system that takes place after the service call is made, we change this to dynamically rebalancing the spatial distribution of responders between incidents. So this is no longer post-incident, this is actually inter-incident planning. So we wrote a paper for AMAS this year, and we came up with two sort of approaches. One approach is a very heuristic queue-based approach. I'm not going to go into the details of it. You can read the paper. The other is sort of a decentralized MCTS approach. Now, why decentralized though? Because the redistribution is a significantly more difficult problem, purely in terms of the extent of the state space, than dispatch. Because it's really not that there's one incident that has happened and you have to dispatch one ambulance. you have to simultaneously come up with a rebalancing strategy for as many responders you have in the field. And you don't really have a lot of time for that because incidents happen fairly quickly. And plus, you have to give the responders time to actually move and rebalance. So most ambulances in the US and all ambulances in our sort of area of concern, Nashville, have fairly powerful laptops attached to them. So we came up with a decentralized approach that can directly run on the ambulance laptop. So each ambulance in its own compute system builds its MCTS tree. But as you can imagine, it needs to estimate what other ambulances will do because maybe my MCTS tree tells me that I need to go to place X, and different ambulances tree also tells the ambulance to go to X. Then there would be two ambulances in the same place, which doesn't make sense. So we have models for how agents can estimate what other agents would do, but they are computationally very cheap, almost constant time lookup models. So what basically happens is that, as you can see in the figure, the rightmost figure, each agent builds its own sort of Monte Carlo tree search tree. Then we have a filter which just does a rough sanity check. So for example, in case something wrong has happened, in case we are sending 3 ambulances at the same place, the filter can quickly tell one of the ambulances to, get rid of its topmost output and go to second best output, so to speak. And then we can quickly do that rebalancing. And then we basically redistribute ambulances according to our predictive model. So we tested this at the Davidson County using simulations. We have a total of 36 fire stations, 26 responders or ambulances, about 36,000 traffic incidents. And then we evaluated our system on about 2,700 incidents. So the visuals are actually fairly complicated in the paper. So I quickly like to share some of the results that we got. What we figured was that inter-incident planning is promising, and it can reduce response times with respect to approaches that do not do any rebalancing. But we also figured that the prediction algorithm is crucial. I mean, if each agent is building a rebalancing strategy using sort of an inaccurate prediction algorithm, then rebalancing not only does worse, it just goes way off. So a crucial sort of piece of the puzzle here is to come up with a really good prediction algorithm. We also figured that local rebalancing works well, and local rebalancing meaning that you don't really ask the ambulances to go across the city for like 20 miles and then wait for an incident to happen. So we restricted sort of our radius of influence to around 3 miles. We actually varied it, but then we saw that 2 to 3 miles is something that works really well. And then we also, ambulances don't, there's a cost for wear and tear. So they don't, and there's also a cost for the, first responders to sit in an ambulance and drive it all day. So we basically had a multi-objective optimization where we traded off the sort of balance between the distance that an ambulance moved and the efficiency that rebalancing achieved. And we figured that that's actually crucial. I mean, if you have exogenous constraints on the total amount of distance you want your ambulances to move, then it can sort of be accommodated into the system. So that sort of brings me to the end of the talk. I'd quickly like to sort of add that I'm currently still working on these problems. I would love to collaborate. If you have an idea, if any of this sounds interesting to you, please reach out. Technically, I'm very interested in sort of spatial-temporal models, robust machine learning, and multi-agent systems. But broadly, I mean, it doesn't, as long as if you want to collaborate on anything to do with, AI for good or AI for environment conservation, or how, we can make smart cities more equitable and more fair to all communities, those are things that from an applied side really draw me. So if you have an idea, please reach out. My email address is there. And thanks for having me. I'll take questions.
Questions? Okay, I have a question. So, so many of the things which you are dealing in this work, both of the work which you describe is the spatial and temporal thing, like especially like ambulance work. But there are many factors like which are unknown in sense, like as you also mentioned, the road can get blocked or something is there, and all of this can definitely affect the model which you are modeling, because in real world the many of such incidents are like somewhat like the unknown environmental factors, you can say that. So how will you take that record, and is it like the algorithm is very sensitive, like if your ambulance reach for somewhat late on the spot, or like if things, if few samples of robustness in terms of like the number of uh, anomalies which can happen in the model kind of
Sure.
thing, any?
Yeah. No, that's actually a very good question, and I mean I could talk about this for a really long time. So let's sort of parse your question into a few parts. First,
Okay.
the thing with emergency response, if you're talking about anomalies, it's we want to look at how many anomalies can happen. We want some sort of theoretical bound. Um, the way these processes take care of that is that they sort of guarantee an optimal response solution. Uh, but then, in order for you to get a long-term optimal solution, you would have to sacrifice something, myopically, which is exactly why post-incident planning does not get deployed in the field, because that simply cannot be done. What rebalancing does is that, compared to an approach that does no rebalancing or no sort of principled decision making, what we can guarantee is that in the long run, this would at least do better. But then the point of anomalies still exists, because we would still have, for example, maybe have to sacrifice a few things on a few, maybe a really small number of incidents, but we want to characterize these anomalies. We want to ensure that that the specific type of incidents that we are losing out on are basically random. That no particular area of the city is getting targeted because of any sort of clearly identifiable characteristics or something. So those are sort of the sensitive areas of trying to work with anything that has direct involvement with citizens. The first part of your question, as far as the algorithms being sensitive to things like road closure and all are considered, there are a few ways how people can handle it. And in our experience, as I said, ambulances get deployed in a variety of places. And I don't mean to do incidents, but they rest at a variety of places, not only fire stations, all sort of major first responders, they rent parking spots. So if there's a huge sports event or something happening, they would just utilize a spot, that is closer to the event, or there's a huge rally or something. So these things are actually very intricately planned, which is why it's very important to make these models online. And I did not go into our work with online models. So you cannot take, 5 days or 6 days to sort of
Yes.
learn and optimize these models. So we have done work on online models, which, you can sort of use stochastic gradient descent, and it takes less than 2 minutes to update these models. So if you have changes in, the road geometry, or if you have changes in weather, you can basically plug that into the model and you can very quickly update it. And usually what responders would do is that they would typically do it every 12 hours or every, 6 hours and stuff, and they would redistribute responders.
Okay. Yeah, it's a complex problem if you look at like multiple factors and also time and space varying. One more question I have, like, so right now most of the thing which you are discussing is somewhat related to human or like a living life kind of thing, and always there is a ethical issues when you deployed AI for human or some human aspect kind of thing. So here, for
Yeah,
example, in the ambulance you are doing resource allocation, and this may actually really, if you have a resource allocation in a particular area or have more resources in a particular area by your algorithm and all, they can always come question of ethic and fairness, like why it may be not good for one community or one area kind of geographic or demographic. So how do you
sure.
can tackle that, and what's your thought about that?
Yeah. Yeah.
This is
Well,
true with the predictive policing thing which you also mentioned while you were talking in the talk.
yeah.
So yeah,
Yeah,
same thing here.
absolutely. So it's actually a way bigger issue for predictive policing than for, ambulance dispatch. It,
Truly agree.
we did some sort of analysis on this. Ambulance dispatch is, there's pretty much nothing as far as biases go. It's a matter of a bunch of incidents, and you want to respond to them as fast as possible. As far as predictive policing goes, most of my work has sort of been to understand how can predictive policing be used to reduce this sort of response times. So once a call comes, how can you place responders to reach the place of the call as fast as possible? There is another aspect of predictive policing, which is, to go on patrols and to look for crime. For example, a random drug stop. Okay. Now, that has significantly higher chance of being corrupt with existing data, because if you have made drug stops at a few sort of biased locations in the city, your historical data is biased, and you're going to keep using that to get more bias. So predictive policing, I mean, I recently wrote a survey paper on this, and it is I think no responder organization should use black box AI systems for predictive policing. We are very far off from having an equitable and fair sort of characterization of how predictive policing algorithms can work. It's significant. The biases, even though poaching is a crime, for example, but coming up with predictive models for poaching does not really face any of these concerns. So I think illegal poaching, human trafficking, smuggling, illegal fishing, logging, these are sort of use cases where all of this is ready to go. We're trying to, Millens, if you know Millens Group, has already done a lot of work in forests in Africa. We are trying to sort of see if any of this can be deployed there. But then as far as doing this in urban areas is concerned, I mean, I don't recommend that, police organizations use this. I think there's just too many moral constraints that sort of need to be evaluated.
Okay. And last question. So also, I feel like many of these models are very dependent on the area or the demographic where you are applying. For example, a model, for example, the New York City won't work for a Utah or Salt Lake City. So what factors do you take in consideration? Like, it's just the features which you change, or there is also change in the algorithmic at any point which you can make things better? Like, for example, I know like the crime will be less in less density areas, so maybe the respondents are less. So what kind of, any thought on that? Like, how will you adapt that model from one place to another, and what changes do you look for?
Yeah, so we actually tried to evaluate this a little bit, and we found that as far as the robustness of these algorithms go, the specific algorithm, the choice of the specific algorithm in question is very orthogonal to robustness. So you can arbitrarily pick an algorithm as long as it has a convex optimization function. You can play around with everything else. It would still guarantee more robustness than the vanilla approach, which is sort of the key point of the robustness. But I've also done work on generating predictive models. We are creating an open source tool which has sort of a bunch of these algorithms coded up and sort of automated report generation. So there are too many factors, as you said. We change the features. If people have to speak to domain experts. It's basically trial and error. You run a bunch of models. You see what is resulting in sort of the highest likelihood on the train set, what is doing better on sort of unseen data. And then you have to come up with there's really no good answer. But I think the people who are the domain experts, and I've collaborated with just so many first responder organizations, I think they have a fair sense of what affects incident occurrence in their
they should be part of the solution, otherwise
absolutely
good. Anybody else have any questions? No. So Ayan, thanks for taking time at such, like, I know it's night there, and have a good night, and thanks for speaking at the group. I will share the video, and thanks a lot. So we cannot have a clap like normal, but we can always have virtual clap. And thanks for taking this time, especially at night. I hope people enjoyed the talk.
No. Thank you, Vivek. Thanks for having me.
And if I have any feedback from the feedback form, I will share with you. And it was a great talk. I learned a lot, and also the complexity of the problem. I understand it much better now compared to, like, I attended Millen talk, but now I understand it's not that, because you explain what the real life things can affect each other, not just at the high level. So that was interesting. Okay. Thanks.
Thanks a lot. Thank you.
Thanks. Thanks everyone for attending. Bye.